Hi, I'm George Pinto, data scientist and machine learning engineer. Well, first of all, thank you all for watching, and I hope that you find this video informative. We're going to talk about convolutional neural networks, and we'll show a use case. Uh, this will be a presentation for executives first, which will show the value of using a dual input convolutional neural network. And then after that, we'll do a presentation for data scientists. And then in this case, we'll show all the gritty details. So the business people are welcome to stay, but it's going to get really intense, we can say, in terms of the design aspects. So this data set was originally used for driven data, a competition that's no longer up. Some of you may be familiar with it because it was originally done for the Microsoft AI Professional Capstone project. I wasn't fortunate enough to even work on this data set at the time because the program, the Microsoft Professional program, ended, and I didn't get to do my capstone. But luckily, we had a chance to choose our own data set for IBM. So on this advanced machine learning class, I was able to do my work on TensorFlow 2, which is very exciting, and using generators. So I hope you guys like it, and we're going to get started. So let's talk about the data set. We had spectrogram images, 1,152 training images, and 768 testing images, sized 128 by 176 pixels. This plug load data set, contains current and voltage measurements, which were sampled at 30 kHz from 11 different appliance types. And basically they were studied throughout households in Pittsburgh, Pennsylvania. And what is a plug load? It refers to the energy used by the products that are being powered by ordinary AC. The energy generated by the appliances basically is being studied, and there's a very good reason for that, which we'll briefly go over in the notebook. But you're looking at energy conservation, so it would be very, very important for government agencies and things like that. So for each of the appliances, the plug load measurements were post-processed to extract a 3-second long window of measurements of current and voltage, and that's what you guys see on the data set, on the images which we'll look at. And basically it shows the transient state when the appliance is turned on, and then the steady state operation once the appliance is already running, and they have different signatures which you can see on the images. For others, it's just a steady state, and then we have 2 spectrograms per appliance, one for current and one for voltage, and this will be important in treating the data set correctly. So here's a use case, which we're going to go over in the notebook as well. But it's the U.S. Energy Information Administration projects a 28% increase in world energy consumption by 2040. So, that's a tremendous increase. It's really a lot. And we need to develop ways of knowing what's causing the biggest impact. And the energy sector is a major contributor to climate change. And so, we're looking at energy production and use being 84% of U.S. greenhouse and gas emissions. So increasing the efficiency of energy consumption has benefits for consumers and providers and the environment. With an increasing number of Internet of Things devices, as you guys know, all these sensors, they're coming online in the energy sector. There's more and more data that can be used to monitor and track energy consumption. Unfortunately, it's a challenge to be able to interpret the data. So we have to find different ways of doing that, so that we can provide consumers, businesses, recommendations in order to save energy and lower costs and help the planet. With that said, in our use case, we need to basically use standard AI tools to identify 11 different types of appliances from their electric signatures, which is quantified by current and voltage measurements. And this is the model. The model takes care of this classification. I hope you guys can see some detail, but basically it has two inputs, one for current and one for voltage, and then out comes 11 appliance types, depending on 11 different classes of appliances, which depends on what images you guys put in there. And it gives you the answers with a loss of 0.5573 and an accuracy of 92.5, which we didn't use all the data, so you can potentially increase that by using all the data that you have and then just training your network with everything you've got, and then getting your prediction from that. You should get an increase on that potentially. So the advantages of this network: we have a dual input model that can be fed the current images and the voltage images, the spectrograms, by easily uploading them on the web, and can be deployed using TensorFlow JS or the user's client's choice of enterprise environment. It's constructed using open source data, Jupyter notebooks, Pandas, TensorFlow 2, and it's built and stored in the cloud. I used Google Colab using GPUs, and stored it on Google Drive, pushed it to a repository on GitHub for version and license control if you need that, which is also very important. And then it's fully scalable because we built it using TensorFlow 2, using generators, which means the model can be fed in batches, and when you need to have a large amount of images, you can easily do that with this type of model. And let's move on now to some of the details. So if you're data scientists, I'm sure you will be very interested, and then if for the business people, you guys are welcome to. So let's take a look at the notebook first. One of the things that I want to make sure that you guys do when you're running a convolutional neural network is to check the notebook settings. Make sure you're using a GPU, and use high RAM, but that's your choice. That's because I needed to get into Colab Pro in order to continue working with a lot of neural networks and not worry about the time, and get a little faster speed with some better GPUs and stuff like that. But then the first thing we do is check the TensorFlow version. You want to make sure it's version 2. So it's connecting, as you can see right here. Yeah, we have 2.3. Then we want to import our libraries, and I still import Keras and TensorFlow, as a backend, but you don't need to do that with TensorFlow 2. Pretty much, some of these things are from habit, but TensorFlow is you can do all the low-level actions, and then Keras is the high level, and it's just pretty much they're pretty much together now. So in one fluid program. Anyway, let's go ahead and import these, and we'll go over some of the details, but we're going to get into a lot more detail regarding the architecture of the model in a second. So you want to put your data set on Google Drive, and then you can mount it here by following this link. And then go ahead and retrieve the password. Oh, it didn't paste for some reason. Let's take a look. Let's just do it directly. Okay, run that. Interesting. Let's try one more time. I don't know why it's not copying. There we go. See if that works. You should see it stop rotating. Okay, it's mounted. And now, you know, you can actually find your data on the drive. And basically, what you're gonna do is copy the path. You know, and then you can place your path here. That way you can retrieve the images from the image folder. And this is the train data, and it's the way the images were stored in driven data. So we went ahead and created a function here for visualizing the images. You can go ahead and run that, and you should be able to see several of the images. And I've also put into the function to go ahead and show us the file name and also the shape. You can see that it's a ping with 4 dimensions, 128 times 76. Let me give you guys a better view so you can see how this is uploading. And this is one of the reasons I have the high RAM, is I like to see all the images, because sometimes you get surprises. You know, you get pixels missing or just the wrong picture file in a folder. You just want to be able to visualize everything that's going on. So let's go through the architectural choices. So you want to start with a basic convolutional layer, one that is widely known to work. Think of VGG16 or Resonant 50, you know, the known architectures known to work really well with images. Take the simplest convolutional block that you can find, and then you can simplify that even further, you know, because there's a flow and logic to image convolutions, and you can always add complexity based on the results that you're getting. So, due to 2 different image types, you know, voltage and current, we're going to need a dual input network. So, my thought about the architecture was 2 networks feeding into one merge layer. Breaking it down into components to simplify the problem, to start working on it. Let's think of one of the towers, one layer at a time. Okay, so here's the code from TensorFlow 2 for the first layer. We can use the sequential model, you know, to simplify it as much as we can. We start with our basic unit, one convolutional layer with 32 filters right here, a 3x3 kernel size, same padding, so we don't lose any of the information from the image. And then we could add a max pooling 2x2 and standard dropout at 0.5 probability. And note that we have a generator input because we want to build a scalable model. For the merge layer, we're going to need to use the functional API, in order to create custom inputs. So we will use the standard flattened, dense, dropout, and an output layer with a softmax activation with the number of classes for the output. So for the size of the first dense layer, we can start by doubling the size of the number of filters in our last convolution layer from the towers. And then we can measure the accuracy for each iteration by adding layers. We can double the filter size. You can see 32 here, then 64, adding blocks as we go along. So this is a double block. And eventually the size is going to have a saturation point. So this time it was a 4-block convolution that created a saturation. So the tower architecture, the two towers with 4 blocks, was about 65% accuracy. In our architectural choices, the first thing we do is increase depth, and see how things look. For these training sets, the results were pointing at high variance and potential overfitting in the training set. So our main concern is to improve the quality of the feature extraction. So if we've gone deep enough, maybe we can check the size of the training set. So we went from about a 70-30 split to about a 90-10 split for train and test. This gets us to about 80% accuracy at the highest peaks, but it's not consistent. Our test loss and accuracy are oscillating widely and plateauing for hundreds of epochs. So the first thing we're going to do is get an early stopping callback so we can iterate quickly and see what's going wrong and try to make some adjustments. You have to have that GPU. It really helps out. So you can see here it's wider and wider oscillations, and then it's plateauing or even going up a little bit. On the test loss, and then the accuracy is also kind of starting to plateau here. It's oscillating widely as well. So our dropout layers should be giving the model a high degree of regularization. So what we need is more stability. We're going to try batch normalization to stabilize activation layer outputs. So you see after these convolutional layers with ReLU activation, we're going to add batch normalization. And then note that the axis is axis -1, which is the color. And we're going to normalize our data. So it's just going to have one channel, but that channel, it really helps out if you check the literature to add batch normalization. So we're going to go ahead and add that. And the stabilization will help with the oscillations, but we still need to consider plateaus. And I chose Atom as my optimizer because I've had previous issues with images, and the adaptive nature of Atom is very helpful with this type of networks. So we'll go ahead and add 2 more callbacks. We'll add reduce on plateau, which is going to make the learning rate reduce every time the gradient descent stops improving. Well, the plateaus basically, so we can see more consistent reductions hopefully in the test loss. And we'll use the parameters that fit Atom the best because we're using Atom. And finally we'll use another callback that saves the best weights only, because we are having those oscillations, so we want to make sure we have the best weights for our model, our final model that we're going to save. So now we have 3 callbacks. We have checkpoint best only, early stopping, and reduce on plateau. So with these choices, we obtain a much steadier, a little bit higher than 85%. But seeing that the oscillations were reduced but still present, I decided to increase the number of neurons in the dense layer immediately after the flattened layer, this layer right here, because that is also known to stabilize the output. and that was very satisfactory. It really helped with the smoothing of the loss curve, doubling the size. So this was the final change in the merge layer. Well, not the final change, but the final size of the dense layer, and we were able to get a lot more stability that way. But then this architecture saw a drop in training speed, becoming sluggish on the gradient descent, and then the accuracy, it would basically stop increasing close to 90%. So potentially a bias problem. I figure one thing that we had not tweaked in terms of regularization could be the dropout. So after several iterations, decreasing dropout probabilities, because we had them all basically at 0.5 probability, we arrived at the final architecture for the towers and for the merge layer. So this is what worked out, starting with a lower dropout probability, and then just gradually increasing. And then the final merge layer, I wanted to make sure that you noted that it did have the batch normalization, and also the dropout was only slightly decreased to 0.4 probability. And now we move on to data quality. So we have high quality 4-dimensional pings of uniform sizes, 128 times 176, delivered in training and testing folders. And there's also a CSV file in there with appliance numbers, which we'll be able to see what we did with that in order to help classification. Additional documentation also was available defining appliance numbers, which we could use. 2 images per appliance, as we discussed earlier, voltage and current. But the appliance numbers, we're not linking those two together, the current and the voltage. So we could use pandas to be able to do that. So you guys saw the data, basically the visualization of the images. That's what they look like. You have your file numbers and then your shape. And here we go. This is the CSV file. As you can see, it had a single ID and the appliance number. And we use pandas to read in. So we can use pandas for data wrangling. And we have our voltage, and we add that string for the voltage, because as you could see here, the appliance IDs are in order, and also they're indexed. So this is very convenient to just add the rest of the number for voltage and current, because we can use that for classification and keep everything in order. So as you can see, voltage and current for each image ID and appliance number. In addition to that, we had information from the original website that went down, and we can get the appliance category names linked to the appliance number, appliance ID. Make this dictionary, and then go ahead and map it out. So now, for both voltage and current, we can make these data frames. You use the category names because Keras already does the one-hot encoding if you give it the category names. So we use the image data generator, and we can go ahead and rescale, normalize by 255. And we select a validation split that works out with the size of our batches. So for me, this worked out really well for the final 90% training, 10% testing that we discussed. So then we go ahead and create the generators, and we're going to create a training generator and validation generator for each of the voltage and current inputs. So for voltage, which is shown here on this page, we use the categories, and then our batch size is 32. Make sure you put grayscale because you're using one dimension. Class mode is categorical, and then the training is subset training, validation is subset validation. Do the same thing for current, and then we need to combine those generator inputs into one output. So I use this function, and you can look at it, and you go ahead and map the function for the training generators and call it combination train and combination validation, also using the mapping the function to the validation generators. And then we use the functional API to be able to make it a dual input and a merged output. And performance indicators. In this case, we compile our model using categorical cross entropy for the loss and accuracy for metrics. And I did 1,000 epochs, but that's really going to stop much sooner with the callbacks. So we fit the model, we use combo train for training, and then for the validation data, we use the combination validation. And you can see here that the fraction that I used is divisible by 32 for both, so it was very convenient to do that calculation beforehand. And these are the results. As you can see, it's a much smoother curve for loss, and we got a final loss of 0.5573, and also the accuracy was much better at a final 92.5. And like I discussed before, guys, if you're getting a test sample, which there was some test data that went with this contest, but the test data was for the contest, so they did not give us any information about the test set. It also had different labels from the original images, so it's something that I can't show you because I don't have the numbers, but you could increase your training by using all of your data for training, and then because you already know that you're getting a 92.5% accuracy, so then you use the rest of the other 10%, and then you do your predictions on your testing data. And this is the final model. You can see how the model is utilizing the callbacks here, and I avoided you guys seeing the first epoch because that's the one that takes the longest. Then the GPU really helps here. You can see it's very low for the time being until we start seeing that that reduction on the plateau kicking in. And you need to configure that according to what you observe, which is based on when you're seeing changes and the number of epochs that it takes. So you set the patience right, and then it will start really helping out. As you can see, it's improving rapidly here. see it very sharply increasing, as we saw on the chart. It's really helping smooth out that curve. See, we're already at 83.8 for the validation accuracy. 5. And I could probably tweak it even more to stop it sooner. But I think this is quite a good setup for this particular network. And it might just take a little bit to get over the last bump there. So as you can see that it's getting very close to having a training accuracy of 1 there. Oh, it's kind of hitting it on and off. Here we go on the last little bit. We're getting to 90%. And it may or may not reach what it had before, or it might do a little better. I think we're gonna potentially stop recording around here so you guys can see that it's steadily improving. And we'll do a little bit of prediction here. So we'll make these imports, and we're gonna take the mapping function again, to map the generators, and we'll do validation, and we'll have the class probabilities based on the predictions. Here are the predictions as an argmax, and the true labels, we'll print them next. We'll print the predictions on top and the true labels at the bottom. And we can see that it's pretty consistent there. Aside from this 2 here that I see, and this 10, 6. A couple of them are misclassified, but most of them are on target. Then just because generators are so much fun, we can go ahead and create this test generators with the test files that I was letting you guys know that they were not labeled, and they had different file names. So we go ahead and create these generators. Again, one for current and one for voltage. We do have those in the test file names. We're able to see the V and the C, so we can tell which one is current and which one is voltage, but they're actually different numbers, different from the ones we had. So let's go ahead and predict a batch, the way we did before. And that's a batch of predictions, just like we did before. Then we're going to get the category names and see what the categories were for that batch. And since we're playing with generators, and like I said, there's so much fun, let's go ahead and use the fact that they're generators to get the full testing predictions. So we go ahead and generate the batch generator, reset it, And then we use from the generator class, we're gonna use that next, and for I in range, the entire length of the generator for both of them, so we could get the full size of the entire folder. And then we get our full prediction. You know, unfortunately, we don't know what they are, so that's one thing. But then, you know, we could see that we could have gone ahead and done really well in the contest. There's the category predictions, and then they wanted the submissions a little bit different. They wanted the ID with the appliance number, so we use pandas for that. So the final submission, we would slice this, you know, and just have the ID and the appliance numbers they wanted. So we would make it look like that. So I hope that you found the presentations useful, and that you enjoy them. And thank you for watching, and you guys have a good one.